Yeah, they always look very precise, yeah. Artist's impression, I'll get to that. That's what the whole focus of this is. So, real absolute pleasure to be here. I think it's 10 years since I was at the last Foresight meeting. Thank you, Alison. Thank you, everybody involved with all the arrangements and organisation. Look at this, it's just amazing. So I thank you, Reza, also for that last talk, because I was getting very worried. I was sitting there going, I don't have a DNA molecule to be seen in my presentation. So I'm going to follow on from what Reza was saying, and thank you for that introduction to STM, scanning tunneling microscopy. I would say getting an array of these things working is great, but the reason I wanted to flag up that point that was so well raised towards the end is the bottleneck is that tip. And this is an artist's impression. That's what we'd like them to look like. And we can, of course, get down to that single atom termination. We can control that, not just down to the atomic level. We can control it to a great extent, actually, in terms of the overall electronic orbital density that's at the end of the tip. I'll explain that. We can do, when I say we, I mean the community, led largely by IBM Zurich in many cases, in terms of picking up individual molecules, individual atoms, and functionalizing the tip. But it is difficult. Any scanning probe microscopist who works in ultra-high vacuum will tell you a great deal of their time is spent trying to coerce or bully or battle with the tip to get it to the state where it will give you single atom resolution or submolecular resolution or whatever type of resolution you need. So, just flagging up Philippe there, and a lot of this is related to his PhD work, and also he's a massive fan of Blender, so some of these 3D rendered images will appear. I don't know if you can see the ghost of Feynman in the top left corner. Of course, we're all contractually obliged to mention Feynman as physicists. This idea of atoms the way we want, and there's been some incredible advances over the last 30 years, a little bit over 30 years. This was back in 1990. I started my PhD in 1990. This was a massive inspiration for me in terms of doing a PhD in STM, and it is still quite remarkable that we can take individual atoms, individual molecules, and move them around. This boy in an atom thing is great, to form out a wide range of different structures and different lattices. We've got graphene-like lattices. This is not graphene, although it looks like it. It's an arrangement of carbon monoxide molecules on a copper surface. You can move those molecules around to form quasi-crystal type structures, Sierpinski gaskets, right across the board. Almost dial in the structure you want. Brian Corrali has recently joined us in Nottingham, and work that he did with his previous group in Radboud University. This was just published last month. I think that's the actual title of the paper. You can dig it out. It was published in Science last month. This is just beautiful, whether you're making artificial atoms out of cesium on an indium antimonide surface. And what you can see is, as they bring these things together, you can see the bonding and anti-bonding orbitals appear. It is really quite remarkable that we're at the point now where we can literally build artificial atoms and image them, not just at the atomic scale, but actually with subatomic precision. That's the question. So why don't we just have a nanofactory? Why don't we have a Drexler-esque, Drexlerian molecular manufacturing capability? We can do it with single atoms. If we get what Wes was talking about, if we get get these all working in parallel, then why can't we do it? And that's certainly been a driver for me. I know some aspects of what Eric Drexler suggested have been disparaged. But that kernel of that idea, can we do computer-controlled chemistry on an atom-by-atom basis, even on a single chemical bond by single chemical bond basis? Yes, we can. But the difficulty is this. Why can't we build 3D structures? There's been so much work on 2D structures. Tips. Controlling that tip. And it's still very much an art rather than a science. Certainly we can get it to the point where we can get atomic resolution and then pick up a molecule, but even if we have a CO molecule, I'm a physicist, anything bigger than a CO molecule I tend to get a little bit nervous and scared of, far too many degrees of freedom. But even with that, it's taken us a couple of years in the AFM community to work out just how that molecule bends on the end of a tip and how that affects the images we see. There's been a lot of artifacts generated by that. So even with something as simple as a CO on a metal tip, still incredibly difficult to interpret. So as I said, mentioned STM. So you saw lots of little things like this. We also do a technique called Q plus AFM, introduced by a guy called Franz Giesebel, about 20 years ago now, I guess. And that allows you to do not just atomic resolution, but get down to submolecular resolution. It's an incredibly high resolution scanning, the highest resolution scanning probe microscope technique we have. And that's largely because we operate in a regime where we push into the Pauli. You think about an interatomic, intermolecular potential, a Lennard-Jones potential, a Morse potential, get into the repulsive part of that, and that interatomic or intermolecular force rockets up for very small distances, very small changes in distance, and that's what you exploit for the highest resolution images and spectroscopy you can do. We've got 7 of these systems, ultra-high vacuum, low temperature, so as far away from DNA origami as it's possible to get. I apologize. But we are working at typically 4 Kelvin, ultra-high vacuum. This one, which is our most recent addition, and we're really happy with it, from a company called Unisoka, gets down to 300 millicale in a 9 Tesla field. So here's that top one, is the set of images up there. This is exactly the same surface, indeed exactly the same sample, and often exactly the same surface region. It's a hydrogen passivated silicon surface, exactly the surface Reza was talking about. We love that surface. In fact, we're currently trying to look at the magnetic properties of that surface. But the top set of images, all of the same surface, and that's what the tip does. So the one here on the left, the ideal one, that's the one we published. That's our representative image. The rest of these are the ones hidden away on the hard disk, or many years ago hidden away in filing cabinets. All the way up to this one at the end. What the hell's going on there? And all of that depends on the tip. So typically in STM, you think you have something sharp imaging something less sharp at the surface, but that, of course, by symmetry is exactly the same as that. So if you have something sharp, such as an electron orbital with a relatively small spatial extent, which is the case for the dangling bond orbitals at the silicon surface, this will image this. And that's what's going on here. You can see that. We can tell from that central image we've got a dimer terminating our tip, or something very much like a dimer. That was a good reaction. Thank you for that. More of those, please. And even again, being the typical reductionist physicist and breaking this all the way down to really simple tip types and really simple tip shapes, the charge density variation is dramatic, even for really small changes in the overall tip structure. And so we can position atoms, we can move them around, we can flip bonds, and that's what's happening here. We're bringing the tip in. The silicon atoms at this particular surface form pairs, dimers, and they have 2 particular orientations, that or that. It's a Jan Teller distortion. I really enjoyed Oppenheimer. It was good to see Teller. But it's essentially a Jan Teller distortion, and what we're doing there is bringing the tip in above the down atom and flipping it up. So you can control it right down, to modify essentially conformation and bond angles right down at that level, but always dependent on the tip. So what we would love is a tip. How much time have I got left, Alison? Probably not much.
Like a minute and a half.
Right, okay. I'll speed up even more. What we want is a self-healing tip. That would be the ideal. Can we find something that, particularly if we want to go to this 3-dimensional assembly, if we want to even build something as simple as a little pyramidal nanoparticle, we want to have something whereby we can drop an atom and then restore the tip. And that involves some type of tricky reversible chemistry, or something as simple as, well, if we drop an atom, does the next one sort of slide down into position? Unfortunately, this is some work from Pavel Jelinek group in the Czech Republic. On their website, you've got these beautiful images where they dropped atoms from the tip. And that's something that we have been looking at for a couple of years now. And here are a couple of examples where bang, 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 you can just drop an atom from the tip. And what's remarkable is you can tell from the image alone, but if I take line profiles through that, the tip resolution doesn't change. Usually with STM, AFM, down at this level, you have a change in the tip structure, the atomistic structure of the tip, And that could lead to a massive change in the overall resolution, or even a subtle change. In this case, it's not even a subtle change. You recover the same tip structure. So what we're very interested in is, can we use this to build structures atom by atom? I'll avoid the pretty, sorry, Philippe, but I'll move on. And of course, this type of thing has been done before many, many years ago, 1990, but these are huge. Okay, those blobs, those are massive blobs. You can see from the scale there, comprising hundreds, if not thousands of atoms. All the way back to Eigler, however, in 1991, they had this reversible switching, reversible transfer from the tip for xenon, I believe xenon and nickel again. The question is, can we build up little structures like this by dropping, instead of sliding them across the surface, but by dropping from the tip? And the answer is, yes, we can. And the reason we're interested in this very simple copper and copper 111 system is that this paper back 20 years ago, almost 20 years ago, from Stefan Folsch and co-workers, there are certain structures, in particular little triangular, these type of structures. It doesn't look triangular because with STM you get a great deal of convolution with the tip, and something that is triangular doesn't look triangular. But we find that this structure cannot be formed directly by lateral manipulation at a temperature 7K. So what they're talking about there is a triangular, just a simple copper 3, a trimer. You cannot make that by sliding atoms together. The potential energy surface is such that you cannot access that. So as a really basic prototypical example of, can we use vertical manipulation to build this? Yes, we can. And that's a trimer. Believe it or not, you might think, hang on, that's a blob. And you'd be quite right to think that's a blob. However, if you pick up a CO molecule, stick it on the end of the tip, this is STM, this is AFM. And that's because the AFM, as I mentioned, has got a much higher resolution, particularly in this Pauli exclusion regime. So the important thing here is that we can build up different structures by dropping atoms. But again, the problem is, I've showed you the stuff that works. I've not showed you the many times where it doesn't work. And I'd say we've got something like a 20% success rate of actually dropping those atoms from the tip. Sorry?
That's not that bad.
It's, well, I'll get you to say that to the students and then watch as they explode. But the question is then, how do we control the tip chemistry? That's really it. If we want to do these amazing, if we want to build structures, three-dimensional structures, and we have then taken an atom and done the most rudimentary structure and put it on top, again, something like a 20% success rate. And that's only for metal tips. If we want to do this for silicon, if we want to do this for diamond, if we want to do this for a wide range of other structures and other materials, how do we control the tip state? And I will shut up. I've gone well over time. Thank you, Alison.
Possible to do some high resolution work in an inert gas like a xenon or argon?
Yeah, in principle you could do that, and in fact obviously many of the early experiments that Eigler did were involved inert gases and moving them across the surface, because then you get a van der Waals interaction with the tip and you essentially slide them across. In our case we're pushing or pulling those atoms. It's a bit of a stronger interaction in terms of at least sliding stuff across the surface. In terms of dropping it off the tip, that's we don't understand what's going on there, and I think it's safe to say in this particular case.
I was actually asking about, instead of going to high vacuum, using an inert gas in a low vacuum or
yeah, that would certainly be possible. Yeah. Do you have a particular system in mind?
No, sorry.
Yeah.
As an expert in approach 4, what do you think of approach 1, using larger things?
It depends on what material you want. So for me, when you look at approach 1, that's very much a supramolecular system. Let's say I want to build a crystal. Let's go back to the original sort of Drexler ideas. If I want to build up a crystal with a particular crystalline solid with a particular band structure, and I want to arrange the atoms. The problem with that is I see it's granular by its very nature. How does that affect electron transport? How does that affect bands in the material? It's very different from this because we're not controlling at the single atom. And I know the Drexler argument is that we don't need to control at the single atom. It depends on what we want to build, obviously. So I don't think it's an either or. It's obviously not an either or. We've got to use a range of these different techniques. bring them together at different hierarchies in terms of how we structure matter.
Were you also able to remove atoms in the Y direction, or only deposit
in the
them?
Z direction.
Sorry, the Z
Depends on how we
direction.
define it. They're all equivalent.
Sorry, video game maker. Y is up.
Yeah. Can we pick them up? Very, very occasionally, even less probabilistic than, even less successful as something like 5%, something like that off the top of my head. What you can do, of course, is what Rezo talked about, is you can inject a current, vibrationally heat up a silicon-hydrogen bond, for example, up to the point where that atom pops off and desorb it that way. But you can, there's a number of examples where, in fact, in many cases with STM, you end up picking up atoms or molecules when you don't want to.
Does the tip still repair if you run it backwards?
There aren't enough examples of, usually what happened in terms of picking it up is that we would lose resolution. You'd end up with a double tip. The atom just wouldn't sit nicely at the end of the tip. It would go to the side and you'd clearly see a double tip, or you'd see a much greater broadening of the features. Yeah.
Have you looked at mounting a structure on the tip, like a tripodal structure that's much more rigid than a CO molecule?
So this is without a CO molecule. All of this is without a CO. So we make these structures, we drop them from the tip, and then we pick up a CO molecule to image it, and then we put the CO molecule down again, and then go on with it. But it's copper, so which is fairly mobile and fairly ductile. It used to be back in the day that everybody would claim that, well, I've got a tungsten tip, tungsten metal, and I etched that to form a tungsten tip, and therefore I've got a tungsten tip in my STM. I think in the very vast majority of cases, that's not a tungsten tip. It's coated with whatever the surface was. I'm not joking.
One more question.
So let's say you get your wish and you could build a 3D structure out of this. Pile of 10 atoms. What's the first thing that you'd want to build, and what's the coolest thing you want to build?
Oh, what a great question. So I would like to look at a doped nanoparticle. I can dope that. So let's take silicon, let's make a cluster of silicon, and let's say I'm going to have one boron atom in that. I'm going to put that boron atom at whatever site I want within that and explore just how that affects, how that dopes the structure and how it's screened. That would be one of the first things I'd do. Thank you for that question.
Thank you.
Thank you.
No problem.